So in the first place, I'd like to thank you for coming and joining me today. I'm here to give a talk about testing distributed systems, distributed applications actually. So let me start with a question. How many of you are coping with distributed applications? Show your hands, please. Okay, I can see a couple of hands. That's good. So my talk is not gonna require any special skills in this area. So no worries, you should be able to understand everything without a problem. We have only 40 minutes, so let me briefly introduce myself to you and then we can start. So, you know my name, I'm working as a senior software engineer at Nokia. I'm based in Wrocław, Poland, and I have started professionally in 2010. Well, I have no plans to retire. I think it will continue to be like this for, if nothing but happens, of course. All of the opinions that I'm gonna express during the talk are solely my own. They don't necessarily reflect opinions of my employer. And I think you may think that I'm not belonging to the picture because I just told you that I'm a software engineer and this conference is about testing and QA. Well, my defense is that for the past 3 years I was doing distributed applications and I really started building those applications, only me, with my own hands. Right now we have about 20 people in the team, so I have really, this was like the most exciting thing that so far happened in my career, and I have learned a lot, not only about the implementing stuff, but also testing it, because once we deployed our application to the cloud, we saw what we are actually lacking from the testing perspective. Okay, and besides that, I am also involved in other stuff, and let me include here some small advertisement. About 1 month ago, we have launched a special kind of escape room in Wrocław, Poland. And you know escape rooms, right? This is a special one that, apart from having some nice background story, also requires from you some IT skills, like the most basic Python skills would be enough. So whenever you are in Poland, especially in Wrocław, then please come play, and I can guarantee that you will enjoy it. So it was small personalized advertisement from my side. Okay, and now about the presentation itself. So this QR code actually points to the Slido. We have 40 minutes, as I mentioned already, and in my presentation, I'm gonna actually tell you what's the difference between, from the testing perspective, what's the difference between single node applications and distributed ones, and why it is fundamentally harder to test distributed ones. Okay, the plan is that I'm gonna start with saying what's the difference, then we'll move to the network conditions and why this is important, then we will discuss fault injection. I will show you one tool, there will be just a short demo, and finally, if we will have time, I will just pinpoint a couple of other difficulties that are apparent if you are dealing with distributed apps, and I will conclude. So let's get started. I was thinking how to lay down the difference, how to tell you what's the difference between distributed apps and single node apps, and it's not an easy task to do, actually. Fortunately, while thinking about it, I was also reading this excellent book by Martin Kleppmann entitled Designing Data-Intensive Applications, and if you are interested in this topic, I can really recommend this one. And in the middle of this book, there was this paragraph, so I simply couldn't resist to include it here. It goes like this. Working with distributed systems is fundamentally different from writing software on a single computer, and the main difference is that there are lots of new and exciting ways for things to go wrong. And I think it gets to the point, also from the testing perspective, because if the application is distributed, it becomes complex, and when it becomes complex, it's also complex to actually test it. This is how it's in the book. Now, let's see how does it look in practice. I will just tell you, because if you are a tester and the application is already deployed to the cloud, let's say, and it's running, and you are trying to break this application with doing some weird stuff to the network, then it indeed can be quite exciting. But I had this opportunity to be on the other hand, on the other side of doing stuff. So I was building my application. Let's call it a baby application. Then I deployed this application to the cloud, so it was making its baby steps, and it was failing after a couple of hours or a couple of days. And even after providing a fix, still the lifetime of this application was extended only a bit. So instead of exciting, it was depressing, I would say. It was so depressing that I even created this device. I call it the cloud wheel of misfortune. So whenever I go to the office, I can roll it and see what today will be broken. Like there will be some network problems, some fluctuations, some outages, and so on, just to release part of my frustration. And just to let you know what we are dealing with, in other script, I just collected all of the network outages and network problems that we had in the environment and put them on the calendar, and this is what I got. The blue item represents some failure, some kind of a failure around the application. So it means that having 3 consecutive days where everything is working fine is almost like a miracle. And if you don't design your application to be resilient to such an environment, then your application not gonna survive too long in the cloud. So what's actually the difference between failure in the cloud, failure in a distributed system, and failure for a single node application? Let's see, because those failures might look similar, but they are fundamentally different. So for the sake of this example, let us think about some application that runs on a single machine. So obviously it will have a CPU, memory, and a disk. And let's assume that the disk fails. I have a disk here with me. It's, disks, right? And what would be your guess? What is the mean time between failure for such a disk? What do you think? Months? Actually, not that bad. But 3 or 4 years. This is maybe not that model, but this is something that you can expect. So you can deploy your application on a single node and then wait 3 or 4 years, and then maybe it will fail. And then what happens? Your application can stop execution, it can crash, and show some message, and it is totally fine, because the contract between you as an application provider and the customer is that as long as the disk is okay, application is also okay. When the disk fails, it means that it's a total failure and the application can refuse to execute. That's kind of obvious. Well, the situation is different when you have a distributed application, because right now you are not running entirely on a single node, you are running on multiple nodes, and it is possible that you will have something called a partial failure. So taking again this disk, if you have a data center, and in this data center you have like 10,000 of such disks, then when you do the math, it turns out quickly that on a daily basis you will need to replace a couple of them. It's just the way things work. So each day you are replacing a lot of disks, and it's quite possible that those nodes will fail and your application is running on those nodes. And a lot of people are referring to this. They say that the failure in a data center is actually a commonplace. And this is quite important thing because it's unlikely that you will experience a total failure, that all of the nodes will fail, but it is also unlikely that the system will be healthy. So it's like in quantum physics, where you can be somewhere in between the 0 and 1 state, and you need to accept this. Also, physics is giving us some other fundamental limits, like the speed of light. And this is another thing that actually limits us. It makes it impossible to create communication channel that will be immediate. So it means that we cannot build a hardware that will solve the problem for us, and this partial failure is actually something that will not go away. So the point here is that we must encode this possibility of a failure within the software layer, and in effect we also need to test this application that it does what it should do, right? And if you stop here and think for a minute, then you can even find some comparisons in the nature around us. My favorite is the brain. We have brains, and brains are like distributed systems. Each neuron is a node. There is a network that connects those neurons together, and then the most interesting thing that is common is that when some neurons are dying, you still continue to live, right? I think you can agree with that, and actually it's quite opposite. So you can drink something, and then your neurons are dying, and instead of dying, you're actually enjoying it. So, but this is also giving us a path, showing us a path how to implement our distributed applications. So even in the presence of partial failures, even if the nodes are failing, then we still have a software that can continue to run, and this is showing us how to build applications. Also, from the testing perspective, we need to be sure that the application can survive such partial failures. They include stuff like network partitions that I will describe in a moment. Also, network latencies. This is quite interesting because as long as the network is fine, application is also fine. But when we have some increased network latency, then there might be a bug that was always there, but we haven't actually thought about it, right? Then we can have some synchronization issues, especially because the communication when the application is distributed is likely to be asynchronous, so the order of messages can be different, and this can also break the application. So we also need to test this. Also, some kind of hardware failures is something that we need to test, and clock-related problems. So if applications rely on the clock, and this is what happens most of the time, then you need to synchronize those clocks across different machines. And if machines go out of sync, then this can cause a lot of problems as well. And finally, actually, last but not least, is the race conditions. We all know that it's hard to write a multi-threaded code that is, working well without flaws. And if you go distributed, it's actually even worse because it's hard to implement something that will be both atomic and transactional. So there are basically a lot of problems with distributed applications, and testing them is also quite a hard task. The point here is that if you go distributed with your application, then you are effectively unlocking the whole new universe of test cases that you need to handle then, and this task is not easy. But in the remaining of this presentation, I'd like to focus on network partitions, why this is important, and then we will see how we can inject a fault into such a distributed application. So how many of you know what a network partition is? Can you show your hands? Okay, I can see 3 or 4 hands. That's excellent. So we have a network like this, and network partition or network condition is a situation in which the communication between some nodes is broken, either entirely or it is just degraded. So in this example, H node cannot communicate with G. This is just an example. Of course, we can have other examples like the H node is disconnected from D and G. But interesting fact is that still the communication between G and H can be done through the I, and this is what the membership protocols in the distributed systems are doing. not to declare H node as it was dead, because it is not dead. We only experience some network problems. Then, of course, we can have other possible scenarios like the network is partitioned almost evenly. This can lead to situations like maybe you're familiar with the split brain situation. And finally, the network can be totally broken and nothing can communicate with anything else. So I think this is kind of obvious what can happen. Now let's go with the stuff that is not so obvious. Like the network problems can be temporary. And maybe you think it's obvious, but if the CPU breaks, if the CPU is broken, then you don't actually think that it will recover, right? If something's wrong in the silicon, then it should stay this way. In the networks, we actually can have situation called network fluctuations. So the latency drops, and then everything is fine again. And it's actually quite tricky because if you want to replicate the problem or find the bug, what's the root cause of the problem, then it's good to have something that some stable state. With the distributed applications, that's most of the time not the case. The second problem is that network problems can be asymmetric. So an example from our production, 1 month ago, we observed that one virtual machine was able to send traffic with full speed, but it was receiving traffic with only 30 kilobytes per second. And apparently, the top of rack switch was faulty in this manner that it was visible in this fashion. That was crazy. Other examples can be either more weird, like the Hadoop file system Jira that I found, where sending small amounts of data over the network was okay, but when they started sending a lot of data, then the switches were behaving weirdly. So as you can see, just disconnecting the nodes from each other, it's quite obvious, but still you might run into weird situations in which it's not so obvious anymore. But the question is why it all matters. Well, when you think about a single node within such a distributed environment, what does it mean? What can be the root cause of the situation that the message was not sent or the reply was not received? Like it indeed can be a network infrastructure problem, that's possible, but also it can be, let's say, hardware failure, like a network card. So far it's obvious it's still either infrastructure or the hardware. Now, what about peer service malfunction? So there is some guy, you communicate with the guy, but it simply, the socket is opened, but the guy will not respond to you. And this is not a hardware problem anymore. Other good example is that the peer is overloaded. So the message is actually waiting in the operating system buffer, and this can either happen to the party that you communicate with or to you. And you have no actual, without some instrumentalization, you have no way to tell that you are overloaded or that you are garbage collected. So it might be that you time out some messages, but actually it's your fault. So this is like kind of tricky. And as you can see, the root cause can be different, and node cannot say what's the real root cause. So it doesn't matter what is the root cause. The thing that we can observe as a node is that the message is not sent or the reply is not delivered. We can't receive the reply. It means that with testing the network, with just breaking the links, we can cover all of those scenarios, and this is what we are gonna do in the next section of my presentation. So let's inject the faults into running system. But let us start with the fault injection. You're familiar with the fault injection. Can you show your hands if you are familiar with this? Okay, so fault injection is like you have a running system, and then you do something on purpose, like you break the link, and then you see how the application behaves. And I was thinking about how to test whether the approach is good. So I just taken etcd database. Do you know this database? It's quite popular, but maybe it's popular when you are building a distributed application. But it's quite interesting because more than 50% of the code in this database is actually dedicated for testing. So I'm sure that the quality of this solution is quite high. So looking at the framework that the guys have built, it's actually something that you can come up with in a couple of days perhaps, or even minutes, depending on your experience. You need to have some kind of tester, orchestrator that will execute the test. Then also, of course, you have this application that you are testing, but the difference now is that the application is distributed and it is deployed on multiple virtual machines. So it's not so easy anymore to test it. And also, this orchestrator must somehow control the cluster, and this is why we have this etcd agent. And the purpose of the agent is like it can disconnect the node from the cluster, it can stress the node, reconnect it again, and do the thing that do all of the things that can happen in the production, but it's all controlled. And then the tester can see that even after the let's say the node was disconnected and some writes were not processed by it, the cluster can reheal itself, recover itself, and still continue to serve requests coming from to the users. But is it easy? What do you think? It's you need to write this piece of code, and you also need to write this piece of code. So it seems like a lot of work to do just to start this kind of testing. And you're definitely not this etcd database, so you need to provide your own implementation. So a lot of effort. So it seems that there must be some kind of easier way to achieve what we are trying to achieve. And maybe you're familiar with Docker. Again, can you show hands? Okay, bigger coverage, that's good. So for the Docker, we have projects like Docker Compose. It basically allows you to run multiple containers simultaneously and then connect them together. There's also this project called Blockade. It basically makes use of the IP tables and TC and other tools available in the Linux kernel and Linux operating system. So it's possible to test some various scenarios without even deploying anything to the cloud. And this is kind of interesting, and it allows you to test your application, test how does it behave without deploying it anywhere. So it's rather simple solution. Maybe you will not stay with this solution for a longer period of time, but at least you will bootstrap this kind of testing if you're not doing this right now. Okay, so now let's have a demo of this blockade solution. I need to do some magic. Okay, so here we go. We are in the shell. So here I have the blockade. It's already up and running, just so we don't have the typing party. And my application is a contrived one because there's no time to do any complex stuff here. So it has Nginx server that will serve the files. Then we have a Redis database and a couple of workers. And then the code is here. Let me just put it on the screen. What the application does? Well, we have this, it's all working with Celery. Maybe you are familiar with Python Celery. So we have those workers, and they will. There is a start function that will call 10,000 times the work function, and the work function will open the connection to the Redis. Then it will increment the enter field. It will then download a file from this Nginx service, and finally it will increment the leaf. So it's like quite simple, right? Nothing magical actually happens here. So now let's see how does it work. So now one more thing. I show those those two fields that are modified in Redis. Now I run this script that will actually monitor what's there. So I just have some auxiliary script that monitors what's the content of those fields, and I haven't yet started, so those are simply not set, right? Then I have this additional script that will execute the task. And now what we see is that it's working fine. It should increment all of those two counters to 10,000, right? Because under the bonnet I have 10 workers with 10 executors on each container, so about 100 workers getting those tasks from the distributed queue and executing them. So if we wait long enough, then it should finally go to 10,000. Okay, and we are done. So it's very fast, right? And let's break it. Let's now use the blockade. I will show you how to use blockade. Let's see the help. What can we do with blockade? We can, apart from normal comments like that are available for Docker Compose, like app destroy, status start, restart, and so on. The interesting ones are flaky, slow, duplicate. So flaky will make network flaky, slow will make network slow. You can just pick some container that you are interested in. Then the duplicate will duplicate the packets in the network, and the fast will bring it up together to the original state. Then we can also do the network partitioning with the partition and join. And the chaos is also a special mode that works more or less like the Netflix Chaos Monkey. Okay, so what I'm gonna do is to slow down the Nginx service. So all of the TC and IP tables magic happens under the bonnet. And now we'll execute this again, and we anticipate that it will be much, much slower. Well, this is not something that we expected, right? The database says that max number of clients was exceeded. What does it mean? If we go back to the code, it means that this request task here is downloading this file, but since the Nginx is so slow right now, it will stuck here. And once it stacks here, it will hold the connection that was obtained here. So we have 100 workers having this connection simultaneously. And also we are running whole Celery through the Redis database. So it means that we have just exceeded possible connections to the database. And how many of you actually anticipated such a scenario while looking at the code? And I'm going to be honest, this is actually the inspiration for this came from 3 weeks ago from our production. There was some faulty component that was leaking the connections. So it was and serving HTTP request was taking the connection, but then it was not closed properly. So after starting our application, after like 30 minutes, we saw that we have 1,000 open connections to the Redis database. What the hell, right? And this is the way you can replicate this with blockade. This is the problem. Okay, so let me get back to the presentation then. Okay, so the scenario was like this. We have a lot of workers, we have a server and a database, and we were actually making damage to this link, but we haven't anticipated that the database will go offline, actually. It will become inaccessible. So it tells us two things, that we forgot about the limitation of the operating system, that when you run some kind of a service, then it can open only up to some limit of simultaneous connections. And the second thing is that this is a single point of failure in our system. And I'm sure that by the end of this talk, the system will not recover because it's already too messed up. So you can really test a lot of weird scenarios with blockade, as you can see. And the cases that you can look for are obviously finding single point of failures, but also connection leaks, like the one that we had with our application. Also, the reconnection handling problem. This was another problem that we have found in our application, that as long as the database was okay, the backend was also okay, but after database went offline and backend was trying to communicate with this database, then even after the database recovered, then the backend was in some weird state and it was not able to for it to work and continue to execute without restart. So, because I already told you that this was running Celery, I was able, in my manual tests, using the Flaky blockade command, to lose about 10 messages, 10 tasks in 10,000 tasks for Celery. So this is something that is hard to actually reproduce, but you need to make sure that if you have a lot of tasks in your system, that they are retried in the application layer. Also, the Python request library that I used here, I think I also managed to break it. It was reporting that the downloads that were incomplete were actually complete. And this is something that I posted on a GitHub for this library. It's quite popular library, so I think it's important. But apparently this is a corner case that nobody runs into, so it's not solved for a couple of months now. And if you think that it's hard to find a bug, you are wrong, actually. Let me give you some example that is a shining one. So, have you ever used BitTorrent? Who never used BitTorrent? Maybe that's okay. One hand. So, what you were likely using was a court algorithm, because it is an implementation of a distributed peer-to-peer hash table. And it was designed in 2001, and after 9 years, some researchers actually found 8 major flaws in the design of this algorithm. So it means even if the software is massively used by users, then it still doesn't mean that it is free of bugs, right? Okay. And if you're interested in how to break distributed databases, I can really recommend this Call Me Maybe Jepsen series. If you type it in Google, then you will find maybe you are interested particularly in some distributed database, and you can just append this database. As you can see, the guy tested a lot of databases, and actually also the blockade that I presented to you was inspired by the work of this person. Okay, so finally, let me just pinpoint a couple of more difficulties, and then I will conclude. The blockade is fine tool, and as long as you are communicating in this part of the communication stack, you are fine, because the containers are communicating with each other, and everything goes through the operating systems and virtual machines. But when you actually start using technology like Docker Swarm, and you also need to test it, or something that is built into the kernel like NFS, then you are unlucky and you can't use the blockade anymore. This is the place where you actually need to consult the cloud provider and see maybe there is a tool that will allow you to play with the cloud network directly. So blockade is definitely not something that will please everyone, but at least you can start with it if you can put your application into the containers. Okay, the second thing that I wanted to tell you is that when you are working with distributed applications, it's not anymore like working with a single pet. With single machine, you can remember its IP address. If you are geeky enough, you can even remember its MAC address. But for the distributed apps, you will not remember all of those details. So you are working, like a butcher. You just destroy the virtual machines and then create another ones. And this is actually a lot of problems boil down to this problem, because it's hard to debug or replicate the bugs. And you need to find a place where it has failed. And even if you find the proper instance, you might find that the instance is already gone. And I'm not joking with this. I have seen a number of times situation like this, that my machines have IP address all consists of zeros. You can't SSH into this. And then you think to yourself, okay, I need to have better logging. So let's talk about logging. If you do logging in distributed system, it looks like, where's the world? It's really, you need to deploy a centralized logging solution, and then it's rather harder to work with, to find what's the culprit in the distributed environment. And it is the same with monitoring performance. When you are doing this on a single host, then it's fine. But for the distributed environment, you need, again, some centralized solution, and it is, simply speaking, just harder. Of course, that's not all. We have stress, load testing, security, chaos engineering, disaster recovery, and final proofs like TLA+. And well, there's a lot in this field, and it is really harder to test distributed applications and prove that they are correct. So coming back to the initial paragraph from the book, it's like there are many ways for things to go wrong in distributed environments and in distributed applications. So with going distributed, you're actually unlocking a whole new universe of weird use cases that you need then to handle. And this is why testing distributed applications is testing level hard. Thank you.